Let's continue our journey into the minds of research chemists as they find out more and more about the chemistry of indoor environments. This, just to remind you, is a 10-year-long research project that would cost millions and millions and millions of dollars. It was not funded by industry. They were really trying to figure out what's going on. And these are all academics talking to each other at this conference. I am Corbett. I am your translator for this. I will be pausing Elliott Gall's session today and kind of digressing on some things that he and I talked about. Elliott is awesome. He was featured a lot in season 3 of Home Diagnosis, which is our series on PBS. If you haven't seen that, please go check that out. This is going to be deep. There's going to be a lot of practical stuff on this one, which I think is helpful because sometimes we get a little bit in the weeds on like, if you've been with us for this whole thing. This is a 31-part series, by the way, if you're just tuning into the first one. There's a bunch that have happened already and a bunch that will happen as well. So anyway, enough said. Let's go ahead and get into it.
Thank you. I'm glad to be here today and have the chance to share some of our work looking at polycyclic aromatic hydrocarbons and how they might be retained on indoor surfaces as a result of indoor wildfire smoke exposure. Okay, so just to frame this, at least initially, how I was thinking about this problem, there's a large body of research that demonstrates that cigarette smoke indoors can create an exposure pathway through interaction with surfaces. Living in the northwestern United States and prior to that Singapore, I've spent a lot of time in smoke-filled indoor environments, as now many of us have. And so that sort of begged the question in my mind, what might that smoke be doing to the indoor surfaces in our indoor environments? How might compounds associated with wildfire smoke associate with surfaces, engage in chemistry, and create, in my opinion, a previously unrecognized exposure pathway?
Okay, now this is called third-hand smoke, what he's describing at the top here. It's not just cigarette smoke, it's also drug smoke. So like meth. If you are ever in a place where they have made meth, it gets into the drywall. And one of the researchers that's part of this 31-week series, Glenn Morrison, had a study that he did specifically about meth homes and what we have to do about it. And his opinion is like, basically it's a teardown at that point. You just got to get the whole thing because it's not salvageable. So that's how much these chemicals that are in the air can then get into surfaces and then come out for a long time and affect the people inside.
And so the work I'm going to present focuses on this question from the perspective of polycyclic aromatic hydrocarbons. When we started this study, we wanted to investigate authentic indoor materials, and we selected 4 indoor materials informed by some of the SurfC work that identified important indoor surfaces or materials. We looked at glass and painted drywall. These were materials that we developed a method for, recovering pHs through solvent-soaked wipes, followed by extraction, followed by gas chromatography with mass spectrometry. We also looked at fleecy fibrous materials, a MERV13 filter, which would be something that would be commonly used in an air cleaning device that would be deployed during a wildfire smoke event, as well as cotton. These materials we directly extracted in dichloromethane and then analyzed that in GCMS following a nitrogen blowdown and reconstitution. So I'm showing some of our results of our method development. This work was recently published in ACS Omega, so there's a lot more details there. Getting pHs off of these authentic surfaces, in some cases, was tricky. We took the extra step of doping our surfaces with a stock solution of a known concentration, and so we could test our method and say how much of each of these 16 pHs we looked at can we get back. I'm showing just 2 of the materials here for brevity. The top material is the recovery percentages we can realize for glass. Can do a pretty good job at recovering the heavy pHs, those with 4 or more aromatic rings. Our solvent wipe the solvent we used is pretty similar. We tried with both IPA and DCM. We got similar recoveries for MERV13 filter and cotton through direct extraction. I'm not showing those results. Drywall we think was interesting. It was unfortunate we couldn't include this further in our study, but we basically could not recover the pHs with our method. So whether there's an issue with our method, we have some data that indicates the matrix might have been interfering. When we solvent wiped paint, we probably brought some of that paint into our sample, but also it sort of indicates that drywall, as was presented earlier today, might be a long-term reservoir for pHs indoors and worthy of future study.
Okay, now drywall and plaster might also have this thing. Like Elliott said, it's probably the paint. And we heard about paint from Vicky Grassian, which is the last session that we just did. The lightweight stuff up here. So they're saying that these polycyclic aromatic hydrocarbons, let's back up for a second. PAH, polycyclic aromatic hydrocarbons, created by combustion, super toxic. It's a class of SVOC compound. So S means semi-volatile organic compound. It means that it's in the air, but it can stick to surfaces. It would kind of rather sit on a surface, but then it'll get kicked up into the air without too much prompting. And the chronic exposure limit for these PAHs is 1,000 times lower than formaldehyde. That's kind of alarming. So these IPA and DCM that you see here in the graph, these are both solvents that they used for the sampling. They're wiping these surfaces, and then they used basically a solvent. They just dipped this cotton and the MERV 13 filter in them to get this stuff out. The reason that they weren't, he thinks that they didn't get these lightweight PAHs out of the glass because of the sampling method they were using. It's called nitrogen blowdown. I don't know what that is, but anyway, I'm not a chemist, if you didn't know that. And I wanted to make sure that everybody knew that these PAHs are not regulated by the EPA. Nobody's paying attention to this out in the world. They regulate stuff like ozone concentrations, and cities have to control pollution, countries have to control. The PAHs, number one, as was brought up in Home Diagnosis Season 3, in episode 1, we talked about fire. You can't regulate wildfires because, like, they're accidents. They're not happening on purpose. So anyway, just wanted to put those things in there.
Okay, so with our method developed, we loaded materials in 2 different ways to prepare for a field study. So we took samples of our materials and we both spiked them with our stock solution where we could elevate the PAH to a very high concentration with a known matrix. We also generated a wildfire smoke proxy in my lab. So we developed a chamber where we can combust pine and cedar needles at above 500 degrees Celsius, where pHs tend to be generated. We basically just smoked these things in my lab, which made me a real favorite with environmental health and safety. So when you tell them you want to make wildfire smoke in your lab, they start to pay attention to you. So we were able to do this for 9 hours per day, and we were able to load these samples with a more realistic matrix of pHs. Our questions: what are the pH mass loadings on these materials as a result of smoke exposure? How long are they retained after we place these coupons of materials in indoor environments and sample them periodically? What do we see? We looked at some cleaning processes to understand if normal, accessible cleaning processes that an everyday person would be able to conduct, can that reduce the pH loading? And then we did a simple exposure scaling calculation to try and understand, is this a meaningful exposure pathway to pHs? We aged our materials in 2 places on the Portland State University campus, one in the interior core of an office that was exposed to only artificial overhead LED lighting. We had another location in that same core of the office, but next to a window that received a meaningfully different type of light and a different quantity. We tried to put samples sort of where they would be logically located. So filter materials were placed under artificial lighting. Cotton, which we thought represented a bed sheet, was placed near natural lighting. Glass was the one set of samples where we compared the lighting conditions. We had replicate samples of glass in both natural light and artificial light because it's known that pHs can engage in light-driven chemistry. We had tested 2 cleaning processes, wiping our glass materials with ethanol or a commercial cleaner, or laundering cotton with a typical laundering detergent, followed by a heating drying cycle. So looking at some data, these are the spiked materials. So again, materials loaded with a stock solution of PAHs, so we're elevating to relatively high surface concentrations on that initial D0. That's when we loaded the material and put it out into the indoor environment. So I'm showing for 4 materials: glass are the top 2, placed in an artificial light location and a natural light location, cotton, and our filter material on the bottom. About 7 times over around 4 months, we collected samples and analyzed them to measure the pH mass that was retained on those surfaces. What I'm showing here are already connected for what we call the negative control. We put out a material that was unadulterated and let it age in the same environment in both locations, and we subtract that off of our measurement. So if a pH background is fluctuating through time, we should be attempting to account for that through our negative control. So you can see that pHs are retained on these materials in substantial quantity compared to a steady state or near 0 concentration, which would imply it's no different from our negative control, for on the order of 45 days, 6 weeks or so. Our glass decay constants, we calculated those for each pH based on our observed concentrations through time, and we calculated first order decay constants to characterize this decay process. We didn't see any significant difference in those decay constants between glass located in light exposed conditions or artificial light exposed conditions, actually natural to artificial light locations. We suspect that's a result of the attenuation of light in the commercial window in our building. I think there's a lot of opportunity for subsequent study there to look at what chemical transformations might be initiated by light relevant to indoor environments. Cotton had the fastest decay. We saw about a 90% reduction in those first 2 weeks from day 0 to day 14, sort of speculating that perhaps ozone in the indoor environment was interacting with cotton in some way, perhaps generating hydroxyl radical near that material that accelerated that decay process. Just speculation. We did measure ozone. There was measurable ozone in this office environment.
Okay, so just to clarify some of what he said, what they did here was they had these spiked, known concentration loaded materials, and then they had clean ones. And they did what, that's the way a microphone works too, by the way, those 3 cables. They took the clean signal and the dirty signal at the end, and they subtracted the one from the other so that they were able to account for, supposedly, the environmental effects of this. However, I'm seeing that like it goes down here by day 37, it's pretty low, but then it goes up again day 58, day 90. And Elliott was saying, yeah, that's probably because of the ventilation that was going on in the space. Like no experiment is perfect, but what I think I understood from our conversation is that a lot of the environmental factors for a wildfire that would have happened in the region in this time frame right here should have been subtracted out. They did still go up for some reason, and that then points to like this idea that Barb Turpin was talking about, where like the more soiled a substance is, the more it picks up. It would react differently. I think that he would agree with that that take on it. The other thing is that the ventilation in this office was where the ozone was coming from. So he mentioned that there was some ozone in the office. That would have been why, is because it's located in an urban area and there's just infiltration and ventilation going on. What you're seeing here with that day 37 being pretty low on everything except for this one right here, it kind of echoes what Joost de Gall also was saying in his presentation, which I'm linking on screen right now, of about this 35 to 45 day lag time on how long you need to wait for these materials to get completely unloaded from all of the chemicals that they absorbed. So Elliott agreed that that's probably a fine time. They waited 133 days just because they had the time.
The filter retained the pHs, which perhaps is logical. It's the most complex porous media that we worked with. We applied those pHs. Perhaps there's ample surface area for partitioning and not being lost back to the indoor environment due to the complexity of that filter surface. We looked at smoke exposed materials as well. And as I mentioned, we were limited in the degree of indoor wildfire smoke that would be tolerated by my institution. And so we weren't able to load materials as high as our spike materials. And I think also that's representative though. So these are wildfire smoke pH concentrations due to 9 hours of smoke exposure at around 150 to 200 micrograms per cubic meter PM 2.5, just to give you some ballpark measurement of the degree of smoke by a commonly used metric that characterizes outdoor wildfire smoke in our exposure chamber. And so you see what we did here is we were near our detection limit for many of these samples that occurred in 45 days and later. And so what we attempted to do is we said, let's take our day 0 concentration, use our decay constants calculated from our spike samples, and see if we can characterize this decay process on a smoke exposed matrix. And it looks like we generally do a pretty good job. You see our R-squared values demonstrate we're explaining a large fraction of the variance. And so we think we can capture roughly the dynamics of a smoke exposed sample in terms of how the pHs are being retained and persisting on an indoor surface. So similar, smoke exposed samples see pHs elevated above negative controls for on the order of 30 to 45 days, depending on the material.
Quickly, this right here is the worst one. And I just wanted to remind everyone that you need to dispose of your filters, because the filter, you could see it goes down, 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 and then it like sneaks up again. And this is something that a lot of HVAC guys will say, oh, well, the dirtier a filter gets, the better it gets at filtering, the more it grabs. But then that's also then bleeding things back into your airstream. So just don't forget, replace your filters.
I mentioned we also looked at cleaning activities, right? So this work was funded by a US EPA grant, which was focused on interventions to reduce exposures to wildfire smoke. So we looked at some sort of accessible opportunities for reducing exposures, including if these pHs are present on materials, how might we clean them to remove those pHs? So I mentioned what those cleaning procedures are. On the top, I'm showing materials that were spiked with our stock solution. On the bottom, those exposed to wildfire smoke. You'll see spiked cotton and exposed cotton. And so laundering cotton reduced somewhere between 48 and 83% of the pH burden that we were able to measure. Again, of this sort of criteria 16 list of pHs. A meaningful difference between smoke exposed cotton and cotton exposed to a standard solution. So an interesting difference there, probably due to the complexity of the wildfire smoke matrix. Glass, we saw a little bit different of a story. We were able to pretty effectively clean glass regardless of the origin of the pHs, anywhere from 62 to 71, or 59 to 71%, depending on the cleaner that we used.
So to be clear, washing with a washing machine will reduce by 83% the stuff that was spiked versus the stuff that was exposed. You're still getting 50%. The point here is don't just wash them once. If you have something like this happen, wash them multiple times and you get like another 83% or another 48% each time you do that. Washing fabric at home is possibly a very powerful indoor air quality method. I said at that point, well, what about your curtains? Like, I don't think I've ever heard of anyone taking their curtains down and putting them in the washing machine, but that probably seems important. And he said, well, because dermal exposure is about what touches your skin, focus on the fabrics that we're in contact with or that we're close to. And that, by the way, would say, like, to me, couch upholstery then becomes a thing. You know, when you're exposed to these really toxic compounds, that might not be a bad idea. So washing, if possible, the cleaning of the glass, likewise, do it multiple times. He said that they used a pretty standard, like what you would think you're doing when you're cleaning glass. And I know that I have 3 children, and when I clean glass, often I'll have to do it a couple of times to really make it look like it's clean. So same thing, just do it multiple times. You get another reduction each time.
Okay, and the last thing I want to mention before wrapping up is we tried to conduct what I will carefully call a scaling analysis to try to understand the extent of exposure that might be realized due to the post-event presence of pHs on indoor materials, right? So the whole premise here is your indoor environment is steeping in wildfire smoke. The outdoor air clears and you take a deep breath and relax. No, wrong, don't relax, right? So what we're trying to understand is what is the magnitude of that exposure? So we constructed a hypothetical model bedroom, said, you know, just keep this simple. For 8 hours of potential exposure each night, when you're sleeping for 7 days following the wildfire smoke event, let's calculate a possible inhalation dose, assuming that the mass loss from the surface is re-emitted back into the air. I have an asterisk there. This is a chemistry group, so obviously there's lots of surface chemistry that could be happening, but this is sort of an upper limit estimate from these materials. We also made an estimate of dermal dose that would be received through contact with a contaminated bed sheet, the cotton that we looked at. And so I'm focusing here on just one PAH in the interest of time, benzoate-pyrene, a known highly toxic PAH, where we estimated the daily dose in nanograms per day through these 2 pathways. So on the left, I'm showing inhalation exposure to benzoate-pyrene with and without cleaning of our surfaces, which included an assumption of wiping down glass, laundering cotton, and replacing the MERV 13 filters in your Corsi Rosenthal box, for example.
Quickly, only the red uncleaned are above the limit, the toxic exposure limit. And those limits are chronic, not temporary. So if you were to come back into this really filthy house and fall asleep on the bed that has still got all these PAHs in it, that one night of sleep is not good for you, but it's not going to be a major problem for your body because, again, these are like chronic things that we're talking about. So once you clean them, both of these fall below the toxic limit. And that below is, again, for the chronic. So hopefully, again, you're cleaning it this day, you're cleaning it the next day, you're cleaning it on day 3, and it keeps going down. And then your chronic exposure becomes much lessened.
So I will say that the daily doses, you know, appear relatively small, less than a nanogram per day, but benzoate-pyrene is highly toxic. promulgated guideline is 0.1 nanograms per cubic meter in air. If you make this assumption of the mass of benzoate pyrene lost from a surface goes into air, you exceed a 0.1 nanogram per cubic meter threshold in this bedroom. Dermal doses are 5 times those daily doses. So there is a meaningful potential for an exposure pathway here, in my opinion. We see a similar story for another pH. I'm not showing a figure, but fluoranthene, we see a similar story. Daily doses of 6 nanograms per day, just on the inhaled intake, due to a 2.5 nanogram per cubic meter increase in room air, again, above an exposure threshold guideline. Okay, so to wrap up, wildfire smoke may load indoor materials with polycyclic aromatic hydrocarbons, and this creates an opportunity for a post-event exposure over a very large population. We saw it this summer that entire regions of continents are exposed to wildfire smoke simultaneously. So we have a huge population that may be subject to these exposures. And a simple scaling analysis just for 3 materials with some big assumptions, but again, only 3 of the materials that might exist in your indoor environment indicates that they might exceed exposure guidelines, which I believe implies the need for further study. Dermal contact appears to be really important for these heavier pHs, at least what we were able to look at in this study. I know folks in this room have looked at clothing as a medium for exposing you to semi-volatile species. Perhaps your smoke-exposed clothing is a pathway for post-event exposure to polycyclic aromatic hydrocarbons. I had that asterisk on my previous slide. I think surface transformations of pHs is something that is a future direction, right? Different indoor lighting conditions, ozone and NOx can drive pH chemistry.
By the way, when they pose these questions at the end, when there are conclusion questions, that means that they're putting in a new research grant. So in fact, Elliott has a research project that is being put together now about this chemistry of polycyclic aromatic hydrocarbons and what exactly they are transforming into.
The sort of wrap up is that cleaning activities, I know cleaning is there's a lot going on with cleaning. Upsides, downsides, at least there is an upside in this case that it appears we can remove pHs with cleaning activities that would be accessible and sort of part of everyone's normal everyday activities. Okay, so I need to thank Aurélie Laguerre, who's moved on to the Salk Institute. She did a fantastic job on this study. We have our methods paper published. Hopefully the paper on this pH field study is under revision. Hopefully that will be available soon. And there's a team of folks assembled for this EPA project that I'm not going to have the time to name, but have really supported us through this work. So again, the US EPA STAR funded this work through what I've called the Hades project, the household atmospheric dynamics under elevated smoke. Hades is the god of the underworld, and I'm sure you can sympathize if you spend some time in a wildfire smoke event. And thank you to the Sloan Foundation for a seed grant that also supported this work.